This. All right, welcome back. Let's see. Can't believe I didn't publish it though. Seriously. How many times have I been doing this? All right, formative assessment 8 it was. That's so funny. All right, preview? Shall we? All right. What kind of information can be inferred from an item characteristic curve in a 2PL model for binary items? This sounds like the world's worst Trivial Pursuit game. Anyone ever sit around in grad school? I was in grad school once, y'all in grad school, playing Trivial Pursuit with your friends. Trivial Pursuit Psychometrics edition. Worst one in the world. Um, what can you find from item characteristic curve? Anybody want to answer? Probably know this already. All right. Item. What is an item characteristic curve? I can wait. Would you rather this or Cholesky decomposition? Correct. The probability of a correct response conditional on ability. So it's just a nice S-shaped curve. Thank you. Appreciate it, Ryan. Do you think sum scores and estimated theta ability scores are interchangeable when analyzing the results of any measurement? So can you replace a sum score with a theta? I like this question. I'm going to just take a drink here. Celsius, anybody? Correct. Yeah, they're not quite the same, right? In the sum scores, you have certain assumptions. Thank you, Erica. Very good answer. A sum score is effectively the result of what a latent variable would be in a parallel items model. It's not exactly the mean of a sum score, and the standard deviation of the sum score is on the metric of the scale, the however you added the items up. So for binary items, it'd be 0 to the number of items. For liquid items, it would be whatever the minimum and the maximum would be per item added together. But in a latent variable model, our ability doesn't necessarily have to have the same assumption. So what am I talking about here? A sum score. To have a latent variable correlate perfectly with a sum score, what do you need? You need a CFA model, right? It has to have an identity link function, so you have to be on the data scale, right? Number two, you need a parallel items model, which a parallel items model is a model where the factor loadings are equal across every item, and the unique variances are equal across every item, right? So if you have those three things, then your sum score and your theta will be correlated at a value of 1. Pretty cool, right? But how often do you have those three things? How often do you run around saying, I'm running the CFA model with all the loadings constrained to be equal? Probably never, right? Only in classes like this to try to get you to understand certain things. So yeah, we can't change them very well. And that's part of the problem with measurement is that um, when you move away from the data, when you move onto this data ability metric, it has its own well-defined scale, but it often is very hard to describe because it doesn't relate to data very well. Um, and I always used to struggle with this in grad school because I like the complicated measurement models, and I couldn't understand why we weren't using them more. And people would say, "Look, the end user, the people who are trying to understand what the result means, can't understand it very well." And so that's sort of the challenge we have. We have a model that fits the data better, most likely, because a parallel items model almost never fits CFAs, and certainly for binary data, right? But the challenge is then understanding what the result means, because now, theta there. True story. Uh, third grade, my son last year here at Wickham Elementary School Coralville, Iowa. His teacher, parent-teacher conferences this time of year, says, here's his FastBridge math score. It's a 209. I don't know what it means. And I say, oh, guess what? You're in luck. His parents happen to tell, we can help you with that. But at the same time, in the absence of a technical manual, 209 doesn't mean anything either, right? It doesn't tell me what proportion of items were correct. It doesn't tell me how difficult those items are. It's very hard to describe. And so this happens quite a bit. So just a heads up. All right. Is this helping? Do you like talking about psychometrics this way? I feel like we're always in technical days, but do we want more psychometrics too? Nah. All right. I'm looking to the side because I've got a new setup anyway. So you're over here now, not over here. All right. We'll just do a couple more. In lecture 4C, we covered different graphs to explore item and test characteristics. Item characteristic curves, test characteristic curves, and information functions. Are there any differences compared to the frequentist approach that you would highlight from using a Bayesian approach when looking at these graphs? Well, my graphs at least. I'll talk about this one. My graphs look all fuzzy, don't they? I have the spaghetti plots. I like to show that way because I like to see the range of uncertainty in these item characteristic curves. So often when we talk about item response theory in a non-Bayesian sense, even in the Bayesian sense, we often just draw the line at our point estimate. But um, that sort of minimizes the amount of error that we might have. And we often neglect to think about the error in the item parameters, but that matters. Quite frankly, it matters a lot when you have limited sample sizes. And depending on where you're doing your measurement work, you might have limited sample sizes. It's fairly common. If you're a student of our program, Educational Measurement and Statistics, often we talk about large scale assessments. So we sort of forget the small sample size side and we sort of ignore and the error is much smaller, as n goes to infinity. But it's for most measurement occurrences, I think large scale assessment, even though it's an industry, like in practice, it represents a small amount of where assessment actually follows if you look at where assessment for research happens to be. And so, for those of you doing assessment and research, is something to think about. Um, excuse me. I should mute myself when I do that. Anyway, all right, I'll stop here. Does anybody want, or do you want me to keep going? Want to go through it? Keep more? Why not? Let's just go through it. When we have binary items and use a logit link function to fit our measurement model, the scale of the data in the model corresponds to. I'm just going to answer this though. Let's see if I can get it right. Scale of the data would be um, Bernoulli, and the scale of the model would be Logit, respectively. How did I do, Vladimir? Did I get that right? All right. This is a check on the mental acuity after being sick last week, right? Getting me warmed up. So I've been in quarantine. My house has this basement where I can kind of hide out so I don't get my, Lisa Hoffman and my son's sick. And this morning I called over to the other side of the house where Lisa's working. I said, do you want me to help you with R? I got to get warmed up for class. And she didn't want help. I was like, all right, fine. So this is my warm up. All right. All right. Inverse link functions are used to, now it's an inverse, right? So a link function takes usually the mean of our observed variable and converts it to the real number line, a quantity that falls on the real number line. Right? So a mean being a probability, we apply a logit, it becomes something that goes from negative infinity to positive infinity. An inverse link function is the reverse. It takes something from negative infinity to positive infinity and puts it back on the scale of the mean, usually the mean of the data, right? So to me, an inverse link function is to go from the scale of the model to the scale of the data. I see Vladimir nodding. I'm going to pass Vladimir's class. All right. And unique variance of the items is not a parameter that is estimated in models covered in Lecture 4C, Lecture 4C being item response models. Because I like this one. In the Bernoulli distribution, the variance is not of interest. For those of you who go out into the world and like if you come from a quantitative method style program like ours and you start working in a program where you're serving and helping others like as a consultant almost or helping students, you'll get that sometimes. Well, I'm not really interested in random effects. It's not really part of my story. I've heard before. It's like yeah, but data don't care, right? The model doesn't care. No, the unique variance can't be there because there's no distribution. There's no place for it. In a Bernoulli distribution, once you know the mean of a variable, you know the variance. So you can't separate the two. That's all. It's weird to think about, but it's there. All right, Vladimir, what's my score? All right. uh, that's a very good distractor. I agree. Turns out, and yeah, so in the Bernoulli distribution, the variance constant. Sometimes, oh, sorry, the variance, there is no variance. I'm sorry, there is a variance. It depends on the mean. But then sometimes when you flip and you're using a logit link, sometimes we add a little variance to the end and it has a constant value. That usually shows up in multi-level designs where you need a level one variance for something. Um, so that was a good distractor. Yes, very good. Very good. All right. We good? Excellent. Who wants to tell me? So before I got sick, it was really not a great lecture, I would say, from my best point, because we started getting into multidimensional latent variable models. Remember that? And oh no, hang on just a second. Let me render this in a different way. There we go. Okay. For a second there, I thought my equations were gone because our studio wasn't rendering it. But thankfully, in the browser, it's doing fine. Um, we got into this idea where we have a Q matrix, right? We have to go and map each latent variable onto each item. That's what the Q matrix does. But with the Q matrix, we can also build stand code to help us build a multidimensional model to estimate these multiple latent variables all at once. And we learned the last time that that stand code is really complicated because of this thing, right? This multivariate normal distribution, right? And we talked about last time the multivariate normal. This is a prior distribution for our latent variables. But it's not just a prior in that we fix hyperparameters to it. We often fix the mean to zero, yes. But for the covariance matrix, we often fix the diagonals to one. That represents the factor variance. But we still have to estimate the off-diagonal values, right? Setting those to zero might put an unnecessary bias on our latent variables as well. So all of that means that we have to take a lot of different steps to go and estimate this thing. And as we saw last time, we tried to embed this multidimensional um, latent variable model in basically with a graded response style item response model, right? So basically, we're taking, remember I mentioned the difference between the theory side and the data side. The right-hand side is the theory side. We're putting our multiple latent variables in here, or better yet, our Q matrix in here to turn on or turn off the values of lambdas that don't need to be in the analysis. And in the graded response model, the item response, everything else stays the same in terms of the cumulative distribution and the difference between submodels to come up with the probability of a different category being selected. So, we could have used a nominal response model here just as well, although it's much more complicated because we have to put constraints on each of the dimensions of lambda. But this model gives us a nice setting to show that we picked this. We could have also gone back to a CFA model, although now that you've learned the graded response model, you don't need CFA for Likert data, right? Right. Hope so. But then we got into the code. Remember this? Not good, right? Um, what made it not good was we basically had to take a few steps, extra steps, to build an estimate for it. First being, um, we have a matrix of thetas, right? Multiplying a matrix of lambdas. This matrix of lambdas is patterned such that it's a zero if the Q matrix is zero, and it's an estimated lambda if the Q matrix has a one in it, right? And we covered, or we're about to cover how we're going to do that today. We left off there. But in the process of doing this, when we have our theta matrix, we actually have to go and describe theta using a multivariate normal distribution. And instead, we use this multinormal Cholesky function. And the reason we use multinormal Cholesky is it allows us to create a correlation matrix that's the Cholesky, what's called the Cholesky factorization of our full matrix. It's a triangular matrix, meaning numbers on the diagonal and below is theta core L. The L stands for the lower triangle of the matrix. Um, and we saw last time that L times L transpose gives us the full correlation matrix back. Does anybody remember why we have to use the Cholesky? I went overboard on this last time. Correct. Yes. Thank you, Ryan. It keeps the same information of the correlation matrix, but because of its triangular shape, the number of calculations needed for the determinant and for the inverse of the correlation matrix are minimized or reduced. And so, therefore, with the number of calculations being reduced, it's thought to be more numerically stable, meaning there's less rounding error. Every calculation you make, there may be a bit of rounding error involved, and the more that we want to reduce as much as we can. So here is our theta core L. It now needs a prior distribution, and we discussed the LKJ prior, Lewandowski. Oh my goodness, I forget what K. Forget it. Lewandowski K and Joe. Sorry, whomever author K was. I'm blanking on your last name. Um, this prior, I'm telling you, this is the best prior in the world for me because it makes it relatively straightforward to do. This may not look easy to you, but prior, again, I keep telling you this, prior to this coming along, it was much, much harder. Okay? Okay. And then everything else, though, the thresholds are the same distribution and the loadings are the same distribution. So remember that? Everything okay? Okay. So I'm not going to go overboard into LKJ or Selesky again. We did that last time. But instead, I want to talk about how we start to build our Q matrix in. Okay? I believe this is where we left off. So I've tried to create stand code to make things easy for you just because I enjoy this type of thing. And I like to try to make it a little easy for you, right? Um, so if you have a Q matrix, you also know how many loadings there are, right? So what I'm going to do in Stan, if I is I'm going to import a Q matrix right here, but I'm going to create in this transform data block, which is a block think I've shown you before today. The transform data block takes your data, transforms it into some form you might need in your analysis, and then allows you to use that form in your analysis in the model statement later on. Right? So transform data gets done one time. It runs before the chains start, right? So you import your data, and then Stan will run transform data if there's a block for it, and then it will start the Markov chains. Okay? So what happens in this block is I can go and define a variable named like number n loadings, which is I need to know how many loadings I have. Why do I need that? Because here, for my vector of all the loadings, it's the size n loadings. But if I have a Q matrix, the number of loadings is simply the number of ones in my Q matrix, right? So what I do is I'm literally looping over each column of the Q matrix, each factor, each latent variable is a column, and I'm adding after each column the sum of the values for that column, right? So I'm adding up the number of ones in that column. So that tells me the number of loadings. Now, the next part's a little bit more complicated. I need to know what I need to build is this lambda matrix right here. Lambda matrix is basically the Q matrix, but instead of a 1 in each spot, it's the estimated loading. So what I'm going to do is I'm storing all of my loadings in a long vector lambda, but I need some type of information to tell me how to go and take that vector and put in the loadings into the right spot into my lambda pattern matrix, right? And that's what that next part of the code tries to do. I'm creating a matrix called loading location, okay? So if you think about a loading, right, the lambda, right, it is going to be a loading that will be, if you think of that lambda pattern matrix, it'll have a row will tell us which item it applies to, and a column will tell us which latent variable it multiplies, right? So what I need to do is I'm going to run through every element of the Q matrix, right here. So I'm going for every row, that's every row is an item, every column, which is a latent variable or a factor. And if that Q matrix entry is a 1, I'm going to save in lambda location its row and column position. Because I need to know that to go and take my lambda element and put it into the lambda matrix. Does that make sense? Sort of? So loading location is an array of integers, right? That is number of loadings by 2 columns, right? So it's 2 dimensions. It has to be an array because Stan does not allow integers to be matrices. Matrices are floating point numbers. So that's why you see array there. And here, um, I'm literally just telling it which row and column each associated loading will have to go into. So I'm going to use this loading location in a different step in the different block of Stan code to go and take my vector of estimated lambdas and put them into my lambda matrix. Okay? Questions? I'm going a little bit slow on this because this is a little complicated. This whole class is a bit complicated, right? All right. Okay. So now that was transform data. Do you remember transform parameters? I think we used that previously. I'm trying to remember where. Transform parameters allows us to reshape parameters we're using in the model block itself. So transform data, remember, runs one time. It happens after you import your data. Transform parameters occurs after every iteration of your Markov chain, right? And that's a difference. Why that's a key difference is because if you think about what we're doing with our lambdas, right? In every step of our chain, we're sampling lambda. So each one of these may have a different value. We're going to have to go and reform our lambda matrix after every iteration. So that's what this step is doing here. So now lambda matrix is defined here, right? And I initialize it with a bunch of zeros. So this rep underscore matrix function basically builds a matrix of the size n items by rows, n factors by columns, and it initializes the values of that matrix to the number in the first argument. And here I'm just letting it be 0. Now I want it to be 0 because remember the lambda matrix will be 0 if the Q matrix is 0. So we want to keep that 0 there. Okay? So lambda matrix, I'll cover that first and I'll talk about theta matrix next. But lambda matrix then, I'm going to go for each loading I have, right? And I'm going to take its row position from the loading location and its column position from the loading location and insert that loading into lambda matrix there. How's that sound? Right. So if I knew for each this loading location that I'm building in transform data, it tells me which row and column each loading should be in. This is sort of taking that vector of loadings and putting it back into a matrix. Cool? Cool. It's a lot, but if you walk through this and see my code, what it means is when you run your multidimensional model, you just have to build a Q matrix and send it to Stan, and Stan does the rest for you. Not bad, right? Okay. Finally, theta matrix. Why do I have to make theta a matrix? Stan, to multiply lambda matrix as a matrix product, right? I need theta matrix to be in a form that allows it to do that. And that's what I'm doing here. Theta matrix is basically taking my theta and making it to a matrix of basically for every column of theta, turning it into a matrix object in R right here. How we doing so far? And this is a bit different, I will say, because theta itself is an array of vectors. Just because Stan will not multiply an array of vectors as a matrix product, because it's an array, even though an array is a type of matrix in normal language. Um, that's why that has to happen. So this is just literally formatting theta to be in the right form to multiply the lambda matrix. And that does it. Pretty cool? I don't know. I don't know if it's cool, but it's a lot. We talk about data then? Actually, let me back up. Questions on any of this? A lot to it. Okay. Um, the data block. Okay. Things that are the same. Item, observations, items, and the maximum categories per item. Remember, in a greater response model, we have to tell it how many categories we have. Y is the same. Again, it's an array. An array has to have integers, and this is Likert data, so the lower is 1, the upper is 5. I set that in there. Next, interestingly, I got lazy in one line. I'm sorry about that. Q matrix I'm importing. The Q matrix, I'm setting the values to make sure they are zeros and ones only. And a Q matrix is an array of integers. Okay? Technically, I could have found, if I found the number of loadings, I could find the number of factors from it. But here I just specified it in code. That's sloppy on mine. But yes, I could have taken Q matrix and in transform data, figure out the number of factors, which is just the number of columns in it, right? Excuse me. The thresholds are the same. This is the prior specification. We talked at length about that before. Remember, this is an array because there's multiple thresholds per item. There's, in our case, four thresholds per item. So it'll be four means in a covariance matrix for each items thresholds. That's why they're arrays. Our lambdas are the same as before, and our mean vector for theta is the same. Here I'm saying this is the prior mean vector of theta, which we normally set to 0. Okay? Okay. Now, another last bit of code, generated quantities. Remember what generated quantities does? It creates statistics of your data after every iteration of the Markov chain, right? Well, we need that to take our Cholesky decomposed correlation matrix and to reform it back into a regular correlation matrix. Because I haven't met someone yet who can interpret the Cholesky very easily. Now, they are out there. Those are people out there who can interpret Cholesky. And I actually think the LKJ folks know quite a lot about Cholesky because that's how they built their prior. But I'm not one of them, so we're going to keep it that way. Okay? We also still, from before, remember Stan uses the threshold parameterization and we convert that to an intercept parameterization. Okay? And if you want to see what this code looks like in R, as you might imagine, this Stan code is quite lengthy, right? Look at all that. We have the data block. the transform data block, the parameters block, the transform parameters block, the model block, and the generated quantities block. That's a lot. We've used Stan to its almost full potential. We just don't have our own user-defined functions yet. But this is sort of the pinnacle of like all the Stan things put together. Okay, so for our analyses, um, this is an old slide. I need to show you how I'm calling it now. The other thing we need to note in a multidimensional model. So here in my slide, why I'm stopping, I'll bet you'll know. I'm initializing my lambdas to be positive again. Remember, we still have that multimodality problem. I didn't initialize theta on this slide, although I should have, because I changed my code to do this. So let's look at my code. Theta now, previous to this point, when we had a unidimensional model, my advice was to take the sum score of theta, add up the raw scores, and standardize it, and then start each person's theta at that value. Well, now we have two thetas. We're going to estimate a two-dimensional model. So instead of having one sum score, we would actually have two, right? One sum score isn't going to help us with two thetas. We have to initialize them in two dimensions. So how do we do that? You might be asking. Ready for some coolness with the Q matrix? So our Q matrix is not found. Of course it's not found. Come on, Jonathan. There's our Q matrix. Can you move that up here? Can you see that okay? Q matrix down here? Okay, there's our Q matrix. Our data file right here, our conspiracy items. Well, it turns out what we need is no longer the total sum score. We need a sum score for each dimension, right? But that dimension, not all items apply to each dimension, right? Only some items apply to the government dimension or the non-government dimension, right? So what we need to do is add together the items where there's a 1 in the Q matrix. Turns out that's a matrix product. All right, hooray, we can use that. If we take our data, turn it into a matrix, so we can do matrix algebra to it, and use this function in this little percent star percent syntax in R, we end up with a matrix where each person's data is multiplying each column of the Q matrix and being added together. And so when it multiplies the first column, where the zeros are, those become zeros in the data. And where the ones are, that's where their value of their score was. And then when we sum them together, we get the sum score just for the items that are indicated in that dimension in the Q matrix. So the Q matrix is really handy also for making sum scores. Sometimes we would call these sub-scores, meaning dimensional scores themselves. But here, if I run that, then sum scores looks like this, right? Our data matrix is number of observations by numbers of items, number of observations by in the rows, number of items in the columns. Our Q matrix is number of items in the columns, number of factors or latent variables number of items in the rows, number of latent variables in the columns. So here, 10 items by 2, 177 by 10 is our data matrix. 10 by 2 is our Q matrix. When we put the two together, we get a 177 by 2 output of sum scores. And that's our sum scores right here. So now what we can do is initialize Stan. There's actually turns out there's a scale function I didn't know about in R. Things I still learn about R, and I've been using R since like pretty much since its inception. This will rescale to make it z-scores. And then we can use that theta init, our z-scores for each dimension, for our standardization for theta. Sound good? All right. Should have put that in my slide. Let's take a look at our results. Ta-da! Boom. What do we see here? An R hat. Let's talk about right there. R hat 1.0667. Do you like that number? You wish it were smaller? Yeah, I can see that. So back in the old days, R hat of 1.1 was good. But in the modern era, R hat, we probably want the R hat to be a little bit smaller. But let's talk about why. Our lambdas are behaving well. They're all at 1, so that's good. We don't have bimodality. Our item intercepts are also behaving very well. This one is 1.01. I'm not really concerned about that. But this value comes from our correlation. Here's our theta correlation. And look at that number. Although I have 993 here. That was a rounding error from one of my first times that I ran it. 0.990. That's pretty big correlation, don't you think? So it turns out when you get a correlation that approaches 1, what's that tell you about your model when you're trying to fit a multidimensional model? Not probably not multidimensional, right? Sorry, Ryan. Is that what I'm guessing that's what you're going to say? Uh, doesn't quite fit. Sorry, go ahead. Yeah, or perhaps overfit, right? Thinking of it this way, what's the difference between how many parameters are different in our model when it comes to what you see on the screen in this multidimensional model versus a unidimensional model? Well, we'd have to see the Q matrix, but we can tell right now there's only 10 lambdas, right? And there's 10 items. So we know that each item still only measures one dimension. So there's no difference in the number of lambdas, no difference in the number of intercepts for the submodels. The only difference is we've added a correlation parameter here. Now, that correlation parameter describes yet 177 new thetas, which we are estimating. So there are a whole lot of new parameters that are out there. But really, from a conceptual point of view, if the correlation was at 1 exactly, this model would basically become a unidimensional model. And what our result is telling us is that it's trying to be a unidimensional model, right? A very high correlation. All right. Looking at that correlation, here's our Markov chain for the correlation. That does not look converged, does it? Probably not. Um, our correlation here goes from 0.94 to 1, but we don't like to see that. And that is our posterior distribution. And if you wanted to look at this a little bit more, let's play around a little bit. What do you think about that? Would you want to try to see what happens if we played with the prior? Want to see if we can make it converge better? Is that danger? Maybe. Personally, if I saw this result, I'd be like, yeah, we have unidimensional data, right? Conspiracy theories are conspiracy theories, regardless of government or not. But let's play for a little bit for the sake of play, because I want to try this out. Why do I do this though? Let me ask you that. Why do I let's I insist on doing things on the fly. It always goes badly. Let's see if today I'm feeling confident today. Let's see if I can make this work better. Um, Going back to the LKJ prior, right? It has a hyperparameter that was defined as this term eta, right? And I set it to be eta being 1, which meant we had a uniform prior on that correlation. If eta were bigger than 1, it moves the correlations towards 0. And if eta were between 0 and 1, it would move the correlations away from 0. So why don't we make eta bigger? Huh? Shall we? Move that correlation towards 0 a bit to see if we can get it to converge. Okay? Now, I hard coded eta, so I'm going to have to change my stand code. And I'm just going to make it 2. 2. Why 2? I have no idea. I don't know what the density looks like. I don't know what it's going to do, but it sounds like a like a decent first to try. So let's try it, shall we? All right. Here comes the fun. Let's see. I'm going to start recompiling. Again, anybody want to take a guess? I was going to say, let's lay odds. How likely is this to converge? Who wants to say it's going to have an R hat that's smaller than 1.06? Anybody? We'll find out. This is the magic of Bayes. You don't like your result? Just tighten the prior. That is what drives everybody who's not a Bayesian nuts, right? All right. Hey, look at that. It's running. It's actually going faster, which means it usually means it's worked. Let's take a look at our R hat here. 1.055. What do you know? And oh, 0.986, and there's our 1.06. So changing it really didn't change a whole lot, right? And if we want to see what that trace plot looks like, that's our new trace plot. And this is the one that we had before. Kind of similar. So what is this telling you about our data? The signal is strong. It's unidimensional, most likely, right? Now, we haven't done model fit check yet, and that comes in our next lecture. But all right, but let's assume, I just want to show some other results with this, okay? Um, First, hey, Vladimir. Yeah, look at, you would think so. Actually, that's a good thought. To be very careful, we would want to do that. Like, actually increase our warm up and sampling maybe here. And let's see if we did that. I'm just going to rerun this. It may take, another minute. We would want to probably rerun this. The reason why I'm sort of skeptical about that is if you look at our posterior plot that's on the chain here, I'm sorry, our trace plot, our time series plot here on the chain of the chains, I'm not seeing any trend except for this is just what's happening. They're bumping up against their upper value. There's no, they've basically converged. It's just this is a distribution that has, where did it go? A shape like this, right? It's negatively skewed. And in a negatively skewed distribution where you're up against a limit, I think this is the type of plot you tend to see in a trace plot for it. But that's only comes from, I can say that because I've had some experience in running these things. But typically, yeah, the first thing you'd want to do is, tighten your prior, run a longer chain, see how things work. We're almost done here. We'll take a look. And I'll save us a little bit of time. Instead of printing the maximum R hat, I'll just print out the parameters themselves. But good thought. Does anybody think it's going to get better? Maybe. We might have a nice, smoother skewed distribution. That's what I think is going to happen. But I still don't think our point estimate is going to come down very much from our upper bound where we're at. All right, let's take a look at the parameter results. 9.86. Oh, hey, 1.02. See, it did get better. Aha, Vladimir to the rescue. Now that's what it looks like. Before, we had a few of these little outlier things. Now we've got more of them. And if you want the density for it, yep, it's a smoother skewed distribution that's up against close to one. How's that work, Vladimir? No, I don't think our conclusion is different at all. I don't know that we have better evidence for it. And honestly, this right here is sort of a this is like the difference between statistical significance and practical significance. And what I mean by that is we technically don't have a model fit estimate of this, right? In model fit, remember there's the two versions of model fit I talked about before. Absolute model fit is indexed by posterior PPMC, and then relative model fit, which is leave one out, or WAIC, like an information criteria. We don't have information about that. And it may be the case that this model still fits better than a unidimensional model with respect to both of those. But practically speaking, a correlation of 0.986 between the two dimensions means there's just so little overlap. Sorry, so much overlap. There's so little unique variation at all, on either dimension, that it's practically a unidimensional model, even if a statistical model fit test would say it's multidimensional. But I haven't gotten. We'll have that in our next lecture. Did that answer your question? All right. Anybody else want anything to play with here? Specs. You've got the code. You can play with it on your own if you'd like, or you can get the code. All right. Other bits and pieces I wanted to talk about was now for each person, like this is person one. Now we have two sets of theta. We have two thetas, right? So instead of having one posterior density of where their latent variable is, we'll have two, or a multivariate density, right? So here, this is the first dimension for theta one for this person. This is the second dimension for theta one. And you'll note this person, their point estimates are very similar. They're close to zero on each of these, right, for their EAP estimates. But take a look at their dot cloud here. This is their posterior density. So what are we seeing in the off diagonal? For every chain estimate, for every iteration, there's a pair of thetas, a theta one and a theta two for each person. This cloud that you see in the middle is that plot of it, right? It's sort of their posterior values of theta, and it gives us a sense as to how correlated they are for this person. And the one thing I wanted to note is just because our thetas are correlated at 0.99, like overall, this person's theta, this person one, their thetas, the posterior estimate of their theta's correlation is actually 0.82. So it's not exactly the same as our overall model parameter, right? Each person may have that. And that's my point here is emphasizing that our correlation matrix for theta is prior distribution, right? This When we estimate theta for each person, we get a posterior distribution of theta. And that posterior distribution of theta is going to be influenced by the prior, but not exact to the prior, right? So for this person, they're at 0.82 for correlation. There you have it. And now, um, this is not for person one. This should be for every person. Uh, Theta one versus theta two's EAP estimates right here. Okay. Theta one versus theta two's EAP estimates. So what do? I have the average theta for theta one, average theta for theta two for each person. I plot them, theta one on the x-axis, theta two on the y-axis. That's where we see that 0.99 correlation. Does that look like a 0.99 correlation to you? How often in your data have you ever seen a scatter plot that looked like this? Hardly ever, right? Maybe? Maybe. Depends on what you're looking at. I guess if you made a transformation of one of your variables and correlated it with the first one, like a linear transformation, maybe. But point I'm trying to make is this is indicating to me there's one dimension here, right? All right. That's multidimensional thetas, multidimensional models. That's what homework 5 that is now out is about. And there's some other features of homework 5 as well too. But the cool thing about this is I've tried to build this syntax again so that you could use it for any type of model. So a lot of this stand code that you have on my screen here involving the Q matrix and transform parameters will be very similar. You could use this in your own work as well. Let me put this back to a 1. Um, you may change the item model sometimes. Like if you wanted the CFA model, this would be normal, right? And you'd have some unique variances. But this whole other process is going to stay a lot the same, right? Okay. Any questions on multidimensional models? I am just barely scratching the surface. The goal of this class is to let you see how to estimate them in Stan. I like to teach a class on a year ago. This last fall, I taught a class on multidimensional measurement models. I like that class. It may be coming back at some point. Um, Literally, there's a lot to multidimensional measurement. Estimation is one of the biggest challenges, and to me, where Bayesian methods really work well is multidimensional measurement models. But that being said, they're not easy, but you're capable of doing it. And you can take my code and use it as a starter syntax, but understanding what's going on in the code also allows you to develop code on your own for your own purposes for multidimensional measurement as well. And that's, I think, a helpful thing is too. All right. In the absence of questions, should we move on to a next topic? Maybe. All right.